So, welcome to week 7 of statistical mechanics, and this is a TA session, which is I'm doing as a part of my PMRF TA requirements. So, I'm Sauravi from IISc, and I'm doing my PhD here. So, in this course, till now, we initially started with thermodynamics and then gradually moved towards the ensembles, okay, which is the statistical description, where we talked about microcanonical, canonical, grand canonical, all these different kinds of ensembles, how in the thermodynamic limit, all of them tend to similar results, okay, and how do you define or find an expression for different thermodynamic parameters starting from the microscopic description, okay, based on this ensemble theory. So that is something which we have been discussing in the last few classes. Till now, when we talked about, system of particles or, a system containing n number of particles, we mostly considered particles which are free, okay, which are not really interacting with each other. So here at the start of today's class, we'll spend some time discussing about what happens when you have interacting particles, okay? And then we would, I hope I'm audible. Okay, so and then we would gradually move towards the quantum mechanical description, which is based on the bracket, formulation, which is like the definition of okay, hello. So at the start of today's class, we'll briefly discuss about what happens when we have a system of interacting particles. Okay. Normally, in the last few classes, we have been discussing about non-interacting particles, where we saw that if you get the partition function for one particle, you can uh, find the partition function for n particles just by a relation. But that holds only when you have a non-interacting system. What happens when you have an interacting system? So we'll spend some time there. And then we will talk about the density matrix formulation, which is the same concept of probability density, what we have been discussing so far, but now in terms of matrices, okay, and which would be very relevant when we talk about quantum mechanical systems, okay. So that's about today's class. Now, typically, this is how the class will go. So we would discuss certain basic concepts and solve certain standard problems. And if there are some doubts, we can try to solve them. So to start with, when we talk about interacting systems, okay, so what happens when you have a non-interacting system? So for a non-interacting system, this is how it looks like. So if you know the partition function for one particle, you know that the partition function for n particles will be given as something like this, right? But now when you have interactions between these particles, there'll be some modifications in, the different parameters of different thermodynamic variables, right? So how will we account for this interaction? So we can start with two major kinds of interactions. One is a hard core potential, one is a soft core potential. What do you mean by that? So for hardcore potential, what it means is if you have two particles, the particles cannot get into each other, right? So it cannot get inside each other. So that means there is a infinite potential for distances below the radius of your particle, right? So the potential is infinity for r less than sigma, where sigma is your typical dimension of the particle that you are talking about. Okay. So that's the hardcore potential. And then on the other hand, you can have soft core potentials where you can have all these different kinds of, examples. One very famous or standard example is the Lennard-Jones potential. It is given as something like this, where this is how it looks like. So there is you would get a minima somewhere around this point. Okay, if this is your distance from the center of your particle, this is how the potential will look like. Now, based on these different potentials, the thermodynamic variables or the equation of state, all of them would vary once you start taking the interactions into account, right? So how do we solve for that? So basically now in the Hamiltonian, initially it was for free particle. Okay, if you have n free particles, we know that the Hamiltonian is given as like t square by 2m, right? But now because you have interactions coming in, you would have an additional term in the Hamiltonian, which is given as summation over ij, I less than j, v of rij. So it's kind of a pairwise potential. Okay. Now, if this is the Hamiltonian, you can actually start by defining a quantity which is given as e to the power minus beta v rij. Okay, so v is the potential that we are talking about, minus 1. And this is what we term as f of ij. Okay, now why are we taking up this form? It will be clear as we proceed. So that this is a mathematical, just some mathematics which actually helps us to simplify the expressions further. Okay, so you can define a quantity Fij, which is given as e to the power minus beta v rij. V is the potential, minus 1. Okay, so now if you want to use the well-known description of partition function, we know this is how it looks like, right? So for indistinguishable particles, the partition function is given as 1 by n factorial, 1 by h to the power 3n. So you're considering 3 dimension. And then you have the base space integral. Okay, and you do an integration over e to the power minus beta h, where h is your Hamiltonian, which is given by this expression here. So till now, when we have solved for non-interacting free particles, we have done a similar process. And there the Hamiltonian was nothing but summation over I pi square by 2n, right? But now you have an additional term which is coming because of the potential, which is this term. So e to the power minus beta summation over I j v of rij, right? So what you can do is basically you can take all the terms which involves the potential, the momentum, okay, and take it out. So basically we already know what this integral is from our already solved question of free particles, right? It's a standard Gaussian integral, so you can solve for that, and this is what you will be getting. Now what is left is the position coordinates, integration of the position coordinates. Okay. Okay, so what we are currently trying to solve is we're trying to see how the partition function or the other thermodynamic variables change when you have interacting particles. So if the interaction between the particles is given by a potential V, then the Hamiltonian is given like this. And then we define a quantity e to the power minus beta V minus 1 as f of ij. So these are pairwise interactions. And then we try to write an expression for the partition function. Now in the partition function, this is the standard definition. So here, whatever we had solved previously was for the free particle, which is just for pi square by 2m. So you can do the exact same calculation, okay? And you would get something like this. So this is for the free particle. Now what is left is the integration over the position coordinates, where you have dr1, dr2, drn, and then e to the power minus beta v of rij. Okay. So what is this telling you? So basically now you have to do a new integration over position coordinates, and where the position coordinates are given, where the position coordinates affect the potential, which is given as v of rij. Okay. Now here what you can do is, because these are all pairwise interactions, you can actually group them as pairs. Okay. Before that, what you can do is, that e to the power minus beta v rij is nothing but f of ij plus 1, right? And you would have some NC2 number of pairs basically, right? Because if there are n particles, you can pair them in NC2 ways. So from there, what you can basically do is now for all these pairs, you would have 1 plus f of 1 2, then 1 plus f of 1 3, dot dot dot. So there will be a product of multiple such terms, 1 plus f ij, right? So this is how the modified expression would look like. So this is coming from the momentum terms, and these are the position coordinates, integration over the position, and then you have a product of all such 1 plus Fij terms. Okay. Now at this point, here you can actually use the, rewrite this further in a very simplified form as something like this. Okay. And now you make use of the fact that if you want to write an expression for the free energy, how would you write it? So free energy will be written as minus kBT ln z, right? This is our well-known definition that we already know. So at this point, you can write F equal to minus KT ln z, and in place of z, you can actually replace this expression, right? What will you get? You would get something like this. Now you can see this looks quite complicated, right? But you would gradually see that we can actually simplify it much further. Okay. So now you can actually define a quantity called pressure. Okay. Which we already know the relation of. So we already know how free energy is related to pressure, right? This is the well-known relation that comes from thermodynamics and from all other discussions that we have had till now. So now once you know the expression of F, you use that to try to find an expression for P. P is a thermodynamic variable. So in you can actually use this relation to find an equation of state as well, right? So what you can do is now you can take this entire description and do a derivative with respect to volume. Okay. So this is how the equation will look like. Till now, you have this product of 1 plus Fij terms, okay, already in the integral. Now, at this point, you can define a quantity F bar, which is given as 1 by n ln 1 by v to the power n, integration of this entire term. So entire this term that you have, you take it as some capital F, okay. So then your expression of pressure becomes much simpler. It becomes n kBT by V, which is our typical ideal gas term. And then you have 1 plus V into del F bar del V. Okay, so that means this term here is this term here that you have is your additional term that is coming because of your interactions. Okay, this is your well-known term that comes from ideal gas. So now you have to solve this further. Okay, and what does it depend on? So it depends on F of Ij, which again depends on the potential of interaction between the particles. Okay, now here what you can do is you can assume that we are at high temperature or at low densities. That means the particles are weakly interacting. So in that case, what you can say is that Fij is quite small. So if you when you are doing this product, okay, so higher order terms you can neglect. You can just take up the first order terms. So that means this entire product can be simplified to something like this. Product of 1 plus Fij for all the pairs can be written as 1 plus summation over all the pairs Fij. Okay. So what you can further do is now you can replace this product by this term here. Okay. So what this is telling you, the first term is nothing but the volume to the power n, right? So this is already there. The second term has the summation of Fij involved. So what is Fij? Fij is nothing but e to the power minus beta v of Rij minus 1, right? So this is a pairwise interaction. So now what you have to use is you have to use the fact that you can just retain two quantities, okay? Out of n, in how many ways can you choose two variables? You can choose it in NC two ways. Now, once you have chosen two variables out of this n variables, and so you have dr1 and dr2. Now you want to see how the potential is between these two particles. So that means what would involve here is nothing but, so you can just retain these two variables and only f of r12 can be there, okay? And all the other terms would contribute to the just a volume term where v is v to the power n minus 2, right? So because you have just chosen two quantities, because you're just looking at one pair first, and then you multiply that with the number of pairs that one can have. This is for one such pair, and then this is the number of pairs that you can have. That is NC2, right? Now you can simplify this term. This still involves two variables, right? So what you can do is you can actually simplify this much further by going to the center of mass frame. So now what you have done is you have n particles and you know that each of the particles interact with a pairwise interaction. So you have said that out of n particles, how many ways can you make a pair? That is NC2. Now for each such pair, they are interacting pairwise. So that means there are two positions involved and the potential involved given as f of rij, right? Now, what you can do now for these two particles, okay, is that you can go to a center of mass frame where you keep one particle constant and then look at what is the distance of the other particle from that one particle, right? Keeping that one particle at rest. So that means you're going to a center of mass frame. So where you can simplify it even further and you can write it as v to the power n minus 1 integration of dr fr. So here r is the distance between the two particles. Initially, dr1, dr2 were the positions. Okay. Here it is the distance between the two particles. And then this is NC2. Okay. So what this is telling you? So this is that's the first term, which is just volume. And then this is about how many pairs you can make. And then you have gone to the center of mass frame. So the only integral that remains is this quantity here. So for any particle, you can just choose one of the particles and in that frame of reference of that particle, okay, at some certain distance r, you know what the potential will be for that particle, okay, and you can just do an integration of f of r dr and then you can multiply it with all such pairwise combinations that one can make, which is given as NC2, and that will give you the interaction term. Okay. So now what you can do is actually you can rewrite as v to the power n plus n square by 2 v to the power n minus 1 integration of dr fr. Okay. So this is still this term here, right? You are just solving for this term. You have to put it in the expression for f or pressure, right? You have to put it here. So how do you do it? So basically now you can write an expression for f, which is given by this relation here. Okay, you can explicitly put the expression now at this point. Okay, now when you put that, what do you see? The higher order terms go away because we are considering that we are at high temperature or low density. The interactions are there but weak. Okay, so then this is how it looks like. You have just replaced the expression. Okay. Now, what you can do is you can use the idea that 1 plus x is close to x is if x is much small. Okay, so that means you can actually replace 1 plus x, this entire term here. This will anyways be ignored. So ln of 1 plus x can be replaced as just x. Okay, so this is how it would look like. Now you know the expression for f. So therefore, you can also find an expression for del f bar del v, okay, which is again basically a derivative with respect to volume. And once you know that, you can put it in the expression for pressure, and this is how it looks like. Okay. Now, what is interesting is that now you have the first term, which is just the ideal gas term, where there was no interaction. And then you have a second term, which is coming because of the interaction. Okay. And there is an integral involved with f of r, where f of r is associated with the potential. And then you have some higher order terms. Okay. Now, what you can basically now do is you can consider n by v as density rho. Okay. And try to write a general expression for pressure. So you would get the first term is the ideal gas term. Then you have a second term which is coming because of the interaction. Then gradually you have all the other terms. Okay, because you're considering at the low densities, it might be just okay to consider till the first correction term, right? Now this entire description is called the virial expansion. Okay, now what is this virial expression telling you? So now basically you have an expansion which defines how pressure gets modified when you have an interacting system. Okay, so here the first correction term or the second virial coefficient, as you would say it, B2, is given as minus of half f of r dr. Okay, what is this telling you? So this is associated with the potential. So that means if you know the interaction potential, you can actually find the virial coefficients. Okay, and in a way, you can put them here to actually find or see how the pressure gets modified as interactions come in. Okay, so now if you are, because you're in the the what do I say, the center of mass frame, basically if you put the particle at the center and consider a spherical region around it, so now you can write dr as 4 pi r squared dr, right? And this is the typical integration that you have to do. So if you now look at certain examples based on what this potential is, you can define the virial coefficients and the expression for pressure or the equation of state from this understanding. Okay, so this is how things get modified when you have interactions coming in. So now based on this, if we try to solve this question, okay, so it says that find the second virial coefficient for particles in square well potential. Find the Boyle's temperature. So now you have a square well potential. So that means you know V. Okay, you can write an expression for V. And then as we have just seen, the virial coefficient involves an integration of f of r dr, right? And f is nothing but e to the power minus beta V plus 1 or minus 1. Just let me see once again. So e to the minus beta V minus 1 is f, right? So that means now you know V. Okay, you have to find f, and then you have to do an integration to find the extra term. That's the second virial coefficient, right? So consider that that means for a square well potential, this is how the potential will be. This is how the potential will be looking like. Okay, infinity at lower values, then somewhere there is a negative, potential, and then it goes to zero. So now for this well potential, okay, can you try to find the second virial coefficient? Okay. The virial expansion by itself is a very standard, or you can say general thing to know. Okay, and whenever you are seeing the video, I'm just giving you some time so that while you see it, you just also try to solve it yourself. So u, or this is nothing but V, that means you know the potential. Now how do you find f? Once you know f, you can do an integration to find the virial coefficient, right? So first point is, how do you find f? So basically, what you have to do is, you know the potential, okay? So now, how do you define V2, which is the second virial coefficient? That is given by this definition here, right? Now, what is f of r? F of r is nothing but e to the power minus beta V minus 1, right? Now, V you know, okay? So you can just put the value of V Okay, and because these are different values at different points, you can just put the values accordingly. Okay, and change as you change the limit of the integral, and then find b2, right? That's what has been done here. So for the first part from 0 to sigma, you have b as infinity. For the second part, you from sigma to sigma prime, you have minus epsilon. And then from the again sigma prime to infinity, it becomes 0. Okay. So now it's a typical integration. Okay. Now once you solve for it, what do you get? This is the expression that you get, right? So this is your second virial coefficient. Now, what is the second virial coefficient? Basically, this is an addition term, or a a modified or I mean a correction term, which is coming because you are now considering interactions into picture. Okay. So if you look at the expression of pressure, okay, this is how the virial expansion looks like. Now, how do you define Boyle's temperature? So if you look at this, virial, where is my? So if you look at the virial expansion, okay. So here we know for Boyle's law, the pressure is constant. So in a way, you know, it should not have this term here. So Boyle's temperature is associated with the point where the second virial coefficient, or you can say the first correction term, basically goes to 0. Okay. So that means in the question, once you know the expression for B2, you can actually set B2 to 0 to find the Boyle temperature. Okay. So for Boyle temperature, B2 goes to 0. So now you can just, remodify it. You want to find the temperature, remember? So that means beta has 1 by kT term, right? So that means you have to write beta in terms of the other terms and then replace beta by 1 by kT. And the T is what you want to find. Okay, so it's something like this. So now for B2 to go to 0, this is how it should look like. From there, you can actually find a expression for the Boyle's temperature. Okay, so this is how it typically looks like. Okay. Now, see, we discussed about ideal gas. Now, once we talk about interactions between gases, okay, so a very standard thing for us to discuss would be the van der Waals gas, okay, where there is some interaction. So from the ideal gas, we gradually go towards van der Waals gas, which is more realistic because there you consider the particles sizes, you consider that they have some interactions with each other. Okay, so now based on our whatever understanding we have had so far, you try to see that how does what if we start with PV equal to RT, which is the ideal gas, how do we go to the van der Waals gas equation, which is as given here, and how does it change when you have 1 mole or n moles, okay, and how do you define the different or from there can you actually get an idea about how the phase space would look like and all this kind of questions. Okay, so this is a very standard thing for all of us to actually know. So here, as you can see, for a typical ideal gas, you would expect this to be PV equal to RT for 1 mole, right? So PV equal to RT. This is what you expect for an ideal gas, right? This is for an ideal gas. Now, there are two major, realistic changes that one has to make. Okay, in nature we don't have ideal gas. So the first point is correction for finite gas, which is like so all the molecules or the particles that are there, they do have some finite size. Okay, so that means the effective area for the particle or effective volume for the particles to diffuse about or move about is not the total volume V, but it is V minus the volume occupied by all these gas molecules or all the particles, right? So that means now V, which is the volume, the net volume of your system or volume of the gas now gets, the total volume gets replaced by B minus B, where B is the volume occupied by the molecules. Okay. Now, the other correction is the fact that there are intermolecular forces. Okay, so that means the particles do interact with each other. Why will it change the pressure term? So you can understand, if you have free particles, you have a container with some wall, the particles go and freely hit the wall, and that is the pressure. That is from where the pressure comes up, right? But now, if you have the particles interacting with each other, there would also be, cohesive forces or forces of interactions between the particles. Okay, so that means the particles are not as free as the case for the ideal gas, right? So that means the force with which it interacts, or the momentum transfer that normally happens for a free particle when it interacts with when it is kept in a container, would be different from when there are particles which are interacting among each other, right? The net pressure with, or the net momentum transfer that happens from the particles to the wall would actually reduce, because there will be an effective inward pull which is coming because of the interactions between the particles, like between each other, right? So that means now, if you want to write P ideal, okay, we know that this is ideal case is this, right? Now, for our case, when you actually have a van der Waals gas in a medium, in a container of volume V, then the effective ideal volume that you have is not V, but V minus B, because the particles do have some size. Similarly, the pressure now is, so when you want to write P ideal will be the effective P, which comes after considering all the interact, I mean, it's the point where you have considered only the effective momentum transfer that happens with the along with the interaction, okay, which is a smaller value, plus some, Pi term, right? So basically now, for when you are replacing, you're writing it like this, your ideal volume becomes V minus B, and your, like, the ideal pressure that you're talking about is actually more than what you expect for a typical, you know, real gas, which has some interactions or interatomic forces. So if this is for the interatomic forces, and then you have an additional term coming in, which is taking into account the fact that in a ideal gas, atoms are free to go and collide with the wall. Okay. So now, what will this pressure term, this term here, this correction to the pressure, what will that depend on? Okay. So you can consider that the force acting on a molecule will be proportional to the number of attracting molecules in the gas. Okay, so that means it is proportional to the neighbors, it's proportional to the molecular density. Okay, and then it is all the net, when you're talking about pressure, pressure also depends on what are the number of molecules that are going and striking the wall, right? So that means it is, as a whole, the pressure is proportional to n square, okay, which is capital N by V whole square. N is the total number of particles, V is the total volume. So Pi is proportional to N by V whole square. Correct? So that means you can now, with this pressure, which was initially there, you have to add an extra term, which depends on the molecular density, or the number density of your particles, as it goes as N square. Okay. So now you can consider that Pi is proportional to 1 by V square, and you can write it as, so this A is some constant. So you write Pi as A by V square. Okay. So now the point is, basically, you have got back this expression, right? This is your van der Waals equation. So you have considered that the fact that the molecules have a finite size, they take a finite size. And then you have also considered that, there is a decrease in the net pressure that is typically there in a real gas, because the real gases do interact with each other, and that pressure difference between a real gas and an ideal gas is proportional to n square, where n is your molecular density. So that means when you are trying to write it in the form of an ideal gas, you have to replace it at the pressure as P plus A by V square. Okay. So once you have this form, now this is your equation of state, right? Equation of state for a van der Waals gas. What do we get out of this? So the first question that we would try to address is, this is for 1 mole of gas, right? So now if you have n moles of gas, how will your expression look like? How will your expression change? Which one among them is the right answer? Okay. So what would change? So first is, if you have, in place of 1 mole, if you have n moles, then the net volume occupied by n moles will be n times B, right? So then that means this will now be replaced by NB, which is all there in all the options. Now the other thing is, obviously, if the number of particles increase or number of molecules increase, okay, that means the interactions will also change, right? The interactions also depend on the molecular density, and it goes as n square, right? So that means from here you can say that when you have n moles, your van der Waals equation should be modified as something like A, right? So because now you have n moles, which you have a n square coming in here, which is coming because of your uh, what do I say? The pressure dependence going as n square. That's the reason. And then the net volume occupied by the particle also increases n times. And here again you have nRT. Right? So this is your expression for n moles of van der Waals gas equation. Gas. Okay. Now the point is that once you have the equation of state, you would always want to see how the phase diagram looks like typically, right? Now experimentally, this was shown by Andrews that this is how the different isotherms for CO2 look like at different temperatures. Okay, so P versus V. Now what you see here is, this is what you get experimentally. Okay, but now if you just look at this expression once again and think, here for one value of P, you would get 3 roots for V, right? So that means theoretically, at this point here, you do not expect a straight. So at this point, you do not expect a straight line like this. Rather, you would expect some, crest and trough kind of thing, so that there are some maxima and minima coming up, right? And that is because you have certain roots. You have, so for each value of P, you have certain values of V where certain roots for V. So that already tells you that theoretically this is not what you would expect, right? This straight line, or what you see within this dotted region, is not what you would normally expect, right? So but this is how it looks like when you have a experimental plot. And here there's an important point where here, beyond which you only get vapor phase, okay, and below which you have this regions of coexistence that comes up. At this point, this is the point where del P del V and del square P del V square, both of it goes to 0. Okay, so this is a critical point. Okay, now if you look at here, so there are 3 roots. Now the point of coincidence of these 3 roots is the critical point of van der Waals gas. What is telling you that while here you can have multiple roots coming up here, once you reach this point, you have one point where the slope becomes 0, del P del V is 0, del square P del V square is 0. So at this point, all the roots become identical. So all the 3 roots become equal. Okay. Now this point of inflection that you just saw, okay, so this point here is defined as the point where del P del V goes to 0 and del square P del V square goes to 0. So now from the equation of van der Waals gas, you can actually write an expression. Where's my marker? So you can actually write an expression for pressure, and then you can try to solve for del P del V and del square P del V square. Okay. Now from here, you can see that if you solve for these two, You can simplify it and write it as something like this. So here, when this happens, so basically when del square P del V square goes to 0 and del P del V goes to 0, that's the critical point. So here the temperature is given as Tc, volume is given as V, like represented as Vc, pressure is represented as Pc. Okay, so these are all critical constants. So now from here, you have gone to here. At this point, what you can do is you can actually solve for Vc between these two equations. And you see that Vc is given as 3b. Again, you put the value of Vc in one of these expressions, you find the expression for Tc, which is given as 8a by 27 Rb. And then you can use this two Vc and Tc expressions in the first expression that you have here. Okay. And from here, actually get an expression for Pc. Okay, so these are the different critical constants of a van der Waals gas. For any other gas or any other system with some different potential altogether, in all those cases, when you're talking about critical, constants, you should look for the fact where del P del V and del square P del V square, both of them goes to 0. Okay, and then from there you can work it out to find what could be the typical critical coefficients. Okay. Okay. Now, what happens physically at critical point? Why it is interesting? So critical point is the point. So here you can see from even from the phase diagram. So above this, you would only get vapor phase. Okay. And here you have some coexistence where there are actually metastable, like super cooled or superheated states as well. Okay. But those are mostly theoretically, like experimentally getting them is experimentally normally you see something like this. So now there is a basically at this point, what happens? Beyond this, there is no, there's only vapor phase. So at this point, there is a coexistence of two phases. Okay, so that's the point where the two phases become identical. So there, if there's a meniscus between the two, phases, at this point it will disappear. Okay, and this is typically associated with something called critical opalescence, where what happens is that the local density fluctuations become too high, which actually changes the local refractive index and the absorption coefficient of the medium. And there is strong absorption and strong scattering, because of which the medium looks opaque. Okay, this is what is called critical opalescence. So again, if you keep on increasing the temperature, you would see that just beyond certain value, your things will again become, transparent. So that means this, in many cases, you do see this case where, there's critical opalescence happening, where basically one would expect that because of this density fluctuation, there's a lot of change in the refractive index, which actually results in a lot of absorption and scattering, making the entire solution very opaque. But it's a very temperature dependent things, because beyond us, if you keep on increasing beyond that or reducing, there you won't get this effect. There it will be a clear solution. Okay. So this phenomena of critical opalescence is deeply associated with this very ideas of phase transitions and what do I say? How do you define phase transition? What are the different features that come up? Okay, at this point, as you can see, compressibility of the vapor becomes infinite. So typically, this kind of critical points are associated with large fluctuations in the order parameters of the system, large density fluctuations. So these are typically what defines your critical point. Okay. So I hope this is clear till here. So till now, what we have been discussing is we discussed a little bit of interacting particles, where we saw how the partition function or the expression for pressure or the expression for different thermodynamic variables, okay, how all of them change when you have an interacting system. Okay, and how does the interaction potential come up there? And then we talked about, van der Waals gases, and we discussed about critical phenomena like critical opalescence and how do you define it in terms of different critical parameters. Okay, what happens at the critical point and so on. Now, at this point, we would gradually move forward, and now we'll talk about something called the bracket representation in quantum mechanics, right? So we are gradually heading towards quantum statistical mechanics, where we would now try to write things in the matrix formulation. Okay. But before starting, we would just give a basic overview of how bracket representation looks like in quantum mechanics, right? This is something which most of you might already be knowing, but for the sake of completion, let us just discuss it for a while. Okay. So what it's telling you is in quantum mechanics, we know that the state of a system is defined by a wave function, which is given as psi, okay, something like this, as you see here, okay. And then there are operators which define the observables. So the operators are things which operate on this wave functions to give you certain measurements, okay. So when there is a operator A and when it is operating on psi, it would result in one of the eigenvalues of the operator, which can be small a n. And then this is how it would look like. Okay. So this is how it would look like. Now, once you make a measurement, the state of the system immediately, collapses to one of the eigenvectors. Now, if you have some quantity, okay, how do you define the expectation value? We'll get to that. So, but before that, now what you can see here is that this coefficients that you have here is actually a measure of the probability of your system to be in the psi n state. So probability of obtaining some eigenvalue is given as this inner product of psi n psi whole square, and then you have normalized it with psi. Okay, these are the different inner products, how you define the probability, how you define expectation value, and so on. Now, if you have a time evolving state, okay, where things are changing as a function of time, what you can do here is you can use the Schrodinger equation, okay, which is given as IH del psi del t is equal to H psi. So H is the Hamiltonian operator, which corresponds to the total energy of the system. So now you can gradually, you'll be able to see that there is a analogy between whatever we have been discussing, or there's a parallel route to what we have seen for the what do I say? The classical case, and now you see the same similar expressions, at least in terms of the concept, similar things which come up in the quantum statistical mechanics as well. Okay, so here what it says is that H is a typical operator that gives you energy, and this is how the Schrodinger equation looks like, talking about time evolution of a state. Okay, now you can define expectation value of any quantity, any operator A. How? So this is what the definition looks like. Okay, so you are doing an inner product of, first you operate A on some wave function psi, and then that wave function you take an inner product with psi. Okay, so and then you normalize it with inner product of psi with each like with itself. Okay, now what we are basically trying to do is, you'd see now, if you can rewrite this further, so you can consider two complete, eigenbases, okay, which is given as this value summation over like all the different values of n for psi n and different values of m for psi m. There are like two pairs. You consider two eigenbases of A, okay, and then from the completion theorem, you can actually put it here, right? Because why? Because summation over m, psi m will be 1, or identity matrix, and again summation over n, psi n, the outer product of this term here would again become an identity matrix. So now what you can write is basically, once you have written it, integral, this term, sorry, so this term here along with this integral would give you nothing but 1. Okay, that's why you can do the replacement. And now what you see from here is you get this extra term which is coming up. Okay, so a closed, sorry. So basically, a inner product of psi n with a psi. Okay, and you know that when A operates on, if A is your operator and psi n is a eigen function of the operator, that means a psi n will give you small a n psi n, right? So that means here only the values where n and m both are equal would survive. So it would look something like this. So here what you can do is you can actually take this an term on the left hand side, and then you have two such pair of inner products, which is nothing but this, right? because n and m are all W variables. So now basically you can write, what are you writing? You are writing A, which is the expectation value of A, as something like summation over n, an, where an are your, eigen values. And then you have this term here, which is inner product of psi and psi whole square divided by inner product of psi with psi. So this term here is nothing but the probability, right? Is nothing but the probability of being in the psi n state. So what you see from here, you see that when you are finding the expectation value, it's actually nothing but the mean. Okay, typically you remember how we calculated mean or average, right? You had, if you have, E1, E2, E3, then the mean energy would be given as E1 into the probability of being in state E1 plus E2 into probability of being in state E2 plus E3 into probability of being in state E3, right? The same thing you're doing here. So you have an all summed over all different values of n. So that means you take into account all the eigenvalues and multiply each of them with their respective probability of being in that eigenstate. Okay. So this is how your expectation value looks like. So you can understand why the concepts are same. We're actually learning to write it in a different form. And this is quite useful when you talk about quantum statistical mechanics. Now, before we proceed further, there is this very important concept of pure and mixed state, and it is very important that you understand this. Okay. Now, what do you mean by a pure state? So, pure means you know in exactly in which state your system is in. Okay. You have some system, and you know that your system is described by a wave function psi. You know for sure this is the state. Then it becomes a pure state. Okay. And if you do not know that, rather you know that there is a probability of being in this state for with P1 probability and then being in the other state with P2 probability and all this kind of things. So then it becomes a mixed state. Okay. Now it's not, so once, one of the students long back, I think, asked me that, do you mean that if you have a superposed state, do you mean that it's a mixed state? That is not necessarily true, right? Because when you write a vector or state vector, or when you are writing a wave function, you can write it in different bases, okay, different basis vectors. So as I will be explaining with some examples, I think it will be much clearer. But till then, let me tell you. So basically, you can write a vector as a superposition of many other vectors, okay, based on whatever basis you are choosing, right? But if you know for sure that this is the combination, if you know that you are in this state, okay, you know the state vector, even though that this state vector can be written as a superposition of different other basis vectors, doesn't make a change, okay? But if you know the state vector for sure that this is the state that your system is in, then it becomes a pure state. So a pure state can also be represented in the form of a superposition of many other eigenvectors. You can do that. Okay. The expression can change based on whatever eigenbasis you are choosing. But the fact is, if you know for sure whatever state you are in, that means you know that this is my wave function and your system is in this wave function with one probability, like full probability, 100% probability. Then it becomes a pure state. If you are in a state where you say that it's in state 1 with 50% probability, state 2 with 30%, state 3 with 20%, then this is becoming a mixed state. Okay. Now, how do you write it? Okay. So you define, now this is interesting and this is important, is how do you define a density operator and what do you mean by that? Okay. So if we look at this here, density operator is given as something like this. So it's telling you that you choose some arbitrary basis, okay, phi k. Now there can be other, so you choose a basis of vectors, okay, and then from there you have one vector phi k, another vector phi k prime, okay, and you say that now you define the density operator as something like this, where there is this row k prime k, okay, and you have this outer product of phi k and phi k prime as written here. Now what is this term telling you, right? So here you can see that if you explicitly try to write an expression for row ik, this is how it would look like. Okay, what is row kk? Row kk is written as inner product of row operating on phi k and then doing an inner product with phi k. This is your expression for row kk. For row k prime k or kk prime, it would be given as something like this. Now, what is this basically telling you? This is basically telling you that you initially had a state phi k. Okay, you used the operator row on phi k to get some state, right? Now you want to do an inner product of that state vector with the initial phi k vector. Okay, right? So this is telling you that this is just the probability for the system to be in the state phi k. Okay, that means you have used this operator on phi k and then taken an inner product with phi k itself, which is telling you what is the probability that your system is in the state phi k. Okay. Now, what does the off-diagonal terms here tell you? So this tells you that again you have a state phi k. You used or you operated it with this row, operator, and then you got another state vector, right? Now, this state vector, you take an inner product with this basic vector phi k prime. So this is telling you what is the probability that your system will spontaneously make a transition from an initial state of phi k to another state phi k prime. So that means this, whenever you are writing this, diagonal matrix elements like diagonal or non-diagonal, you are basically like all the row k, k or row k, k prime terms, the terms in the density matrix. Okay. So all of these are actually talking about probability of either being in that state, which is the case for the diagonal terms, and the probability of going from one state to another, which is for the off diagonal terms. Okay. So now based on whether you have a mixed state or a pure state, you would get different matrix elements. The elements might also vary will also vary based on what basis you are choosing. Okay. So that means now if you consider a pure state, okay, so if you prepare your system such a way that it's in one of the states psi I with some probability pii, okay, and pik goes to 0 for I not equal to k, okay, then what happens? The density operator becomes diagonal. That means you're saying that all the off-diagonal terms are 0 in the density matrix. So what happens then? Then you can actually simplify this further to write it as something like this. So now you only have a summation over I. Only the outer products with the same state vector survive. Okay. Now, if it is a pure state, that means there is no summation involved. It's just in one particular state. Okay. And it is in that state with 100% probability. So that means PII is 1 for one index I and it's 0 for all the others. Okay. So that means for a pure state, now your expression of your, density operator looks something like this. Okay. Your system is in psi state. So outer product of psi with itself will give you the density operator. That's for a pure state. For a mixed state, again, you would have this kind of a summation involved. Okay. Now, what are the different properties of density matrix? So density matrix, the terms of the density matrix is associated with the probability of being in those different states. Okay. So now for a pure state, you saw that if the state is defined as psi, then the density matrix. So then the density matrix is given as outer product of psi with itself, right? Now there are some interesting properties of density matrix. What we see is if you now do rho square, okay, so square of the density matrix, you can write it as something like this. Now you know that for a normalized, state vector, okay, so inner product of psi with itself would actually give you 1, right? So that means you get back the same expression, which is rho. So that means for a density matrix, pure state, density matrix, rho square is equal to rho. So for any given state density matrix, or for any system, if you can find the density matrix and if you see that rho square is equal to rho, then it is a pure state. Okay. Now you can also take the conjugate, okay, Hermitian conjugate, and this is how the conjugate will look like. So you would see that the conjugate is equal to the density matrix itself. Okay. And then you can also find trace of rho. What is trace of a matrix? Basically, you're doing a summation over all the diagonal terms, right? So what you can do is you can do something like this. You can write it as something like this. This is your whatever, matrix that you are talking about, but you only want to look at what are the diagonal terms. So now you can do a summation of this inner product, right? Where n is a complete orthogonal set of state vectors. So now because it's a complete orthogonal set of state vectors, you can write, that summation over n, outer product of n with n, this will give you 1. So you can just rearrange these terms, okay, take this to the left hand side, you would get a term like this, okay, which would give you 1. So you would get back this expression. Okay, so for a pure state density matrix, trace of rho goes to 1. Okay, now if you know the density matrix, you can also try to find actually the expectation value of an operator. So suppose you have some operator A, okay, and you want to find the expectation value of the operator. That means some average, value of that observable. How do you do it? So normally we know that this is how it looks like, right? If your psi is already normalized, this is how it looks like. So now what you can do is basically you can write it as, because this forms an orthogonal set of state vectors and this summation goes to 1, you can actually put it here, right? You have just put identity matrix basically, right? So anything multiplied by identity remains same. So you can always multiply by 1. So now once you have done this, you can actually rearrange it further and you would see that what you have now got, okay, so once you write it like this, what you have now got is actually trace of this quantity, right? This matrix. So that means when you are doing expectation value of some quantity or some observable or some, operator, what you are basically doing is you are trying to find the trace of that operator or that matrix, which is along with a product. So product of rho, which is your density matrix, with that operator, okay? And then you get a new matrix and then you find the trace of that. That by itself will give you the expectation value or the average value. So basically the same thing you are now learning or trying to see how you can write it in terms of matrix formulation, okay? Okay. Now what happens when you have a mixed state? So for pure state, you just had one, state, psi. Now you have I number of states with each of them with probability pi. So that means your now the density matrix will look like summation over I, pi, and then for each such state, you have this outer product psi, and multiply it with the probability, corresponding probability pi, and do a summation. This is your mixed state density matrix. Okay. Now, how does this different, what are the different properties that it shows? So again, if you do the Hermitian conjugate, you would see that it remains same. So the Hermitian conjugate is same as the density matrix itself. Okay. But now when you do rho m square, so the m subscript that comes up here is because of the mixed state. Okay. So rho m square is nothing but, product of two such things, like where I and j are dummy indices. So now you can explicitly write it. Okay, you can write it further and rearrange it. So what will you get? You would see that you have pi pj and then this term here. Now what is this term telling you? That this will be non-zero only when I is equal to j. Okay, because you are talking about orthonormal sets of orthonormal basis of vectors. Okay, so now what you can do is I and j are dummy variables basically, and you have this delta ij, so that means I must be equal to j. Only then this will be non-zero. So that means you can remove one of the summations and you can write it as summation over I pi square psi I psi I. So you can understand this is not the same as this, right? You have you had pi here, you have a pi squared here. It's not the same. So that means for a mixed state, the square of the matrix is not the same as the matrix. So if you are just given a random density matrix and asked whether it is representing a pure state or a mixed state, how will you find it? So for a pure state, rho square should be equal to rho. For a mixed state, rho square is not equal to rho. Okay, that's a very mathematical way of looking into it. Physically, when you know the entire, with 100% probability that your system is in this state, then it becomes a pure state. If there are, there's an ambiguity, so you know that it can be in certain state with certain probability, then what you are describing is a mixed state. Okay. Now, similarly, you can try to find the trace of rho. Okay. And even here, you would see that the trace of rho would go to 1, while the trace of rho square is not equal to 1. Okay. And then you can also try to find the expectation value, which will again be the trace of this density matrix with that operator. Okay, so do a product of the density matrix with the operator and find the trace. That gives you the expectation value or the average, measurement value that comes from that operator. Okay, you can explicitly write it. Okay, so if you explicitly write it, this is how it would look like. Now, because it's a trace, you can write it as a summation of these terms, okay, and then rearrange it further. Okay, just taking pi out of it here, and then what you can do is you can put in new what do I say? Put in the fact that your shies are orthonormal sets of vectors. Okay, so you can put in new summations and rearrange the terms. And then this is what you will be getting. So that means it is again, you see the probability of being in that state and then the value. Okay, it's the same concept. So once you know the density matrix, you can actually find average value or expectation value for any observable, you know, operators or any observables. Okay, just by doing a product of the operator matrix with the density matrix and then trying to find the trace. Now, based on what we have been discussing so far, if we now try to understand or answer this question, so you says that you have a system of spin half particles. The state of the system is defined as 1 by root 2 up plus down. Now, is it a pure state or a mixed state? Okay. So based on whatever we have been discussing, okay, I am just giving you a couple of minutes to think before I actually tell the answer. There are two basis vectors here, right? You have a up and a down. And then you say that your system is in a state which is given as psi, which is 1 by root 2 up plus down. So see here, basically this, the very mathematical way of doing it will be that you know psi, okay? You know how to, if you know psi, you know how to write rho, right? So rho would be written as something like psi. You just know about one state. So you can try to find this. So you can try to find this. 1 second, sorry. So basically, you can try to find rho, which is nothing but the outer product of psi with itself, right? Because you are just given information about one vector, one wave function. So if you do this, Okay, mathematically I'm saying, if you do this, okay, you do the outer product, and then you see, you also do rho square. You would get a matrix from here, right? And then do a product, do a square of the matrix. So this is how it will look like. See if rho square is actually equal to rho or not. Okay. If they are equal, then it's a pure state. If they are not, then it's not a pure state. That's a very mathematical way of doing it. Okay. Just give me 1 second. 1 second. I have I'm sorry, that was a call that I had to take. Okay. So now what this is telling you is that here for this question, you basically know that your system is in state psi. You can find the density matrix from here, which is nothing but doing an inner outer product of psi with psi. Okay. And then from there, you can see if rho square is equal to rho. If it is equal, then it's a pure matrix. Otherwise, it's a mixed state. That's a very mathematical way of looking at it. But even before that, from the fact that you already know that your system is in this state, okay, it's telling you that it's a pure state. Okay. Why? Because see, for the particular basis vector, here the basis vectors that you have chosen is up and down vectors, right? Now, for this basis vector that you have chosen, you have written another vector as a superposition of these two basis vectors. Okay, so that is absolutely fine. But then you exactly know that your system is defined by this state. Okay, you are in this state with 100% probability. That's what the question is saying, right? So that means this is a pure state. Later, when I'll show more examples, I think it will be even clearer when we will have a mixed state and a pure state. So now that means the system is defined by a single state psi. So it's a pure state. Now, how do you find the density matrix? So basically, you have to do an outer product of psi with psi, right? How do you do that? How do you do an outer product of psi with psi? So psi is explicitly written as half of up plus down. And then, so this is bra, this is kate, right? So then again, so 1 by root 2, 1 by root 2 gives you half. And then you have a product of this with this. Okay, explicitly, if you write it, you would get all these 4 terms, right? So now, if from here, if you want to write it in a matrix form, how will you write it? This is the form, right? This is the form of your density matrix. Now, you have to write it in a matrix form. So you have to look at how the product terms are. Okay. So if you look at this combination, right, from here, if you look at this combination, this is nothing but this, right? Basically, what you have done, you have taken, so for this particular, description, we have chosen a basis vector of up and down. And now you, in one side, you take a bra, in other side, you take a ket, okay? And then you put in this term here, this matrix here, which would give you this form, right? And you see that this, what is this telling you? All of these terms, okay? If you multiply with half, all of these terms is giving you half, 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 right? And these are nothing but these coefficients that you have here, right? The coefficient for all of these 4 terms is half. And that's what also comes up here, right? So that means now what you can say is that my density matrix is defined as this matrix half into 1, 1, 1, 1. Okay. Now what you can do is once you find rho, you can actually find rho square. Okay. And see if rho square is equal to rho. And you will see that rho square is equal to rho. So then it mathematically also proves that it's a pure state. How do you find the trace? So trace of the density matrix is nothing but, so if you know the matrix now, trace means summation over the diagonal terms, right? So half plus half, which is 1. So trace, and anyways, we know from our previous discussions of the properties as well, that trace of a density matrix is always 1, right? So that means the third answer should be 1. Now here you can ask me that, you have all these different terms here, so why isn't this a superposition, or why isn't this a mixed state? So the point is that this is in this basis that you have chosen, the up and the down vectors. In so if one, that means when you have chosen the basis vectors to be the up and the down vectors, then you have this form of your density matrix. This does not tell you that your system is in certain state with certain probability. Your system is in this state with 100% probability. Okay, a single state. So what would happen is, now if you try to diagonalize this matrix, this is some matrix, right? So if you want to diagonalize this matrix, what you would see is that for certain combinations, what would come up is that you would have a non-zero term somewhere here, and all other terms would go to 0. So that means you can actually change the basis vectors, and you can see that when your basis vector is actually defined by some quantity like this, okay, if you choose this as one of your, if you choose psi as one of your basis vectors, in that space, your rho will have only one non-zero value, and that non-zero value will be 1. So it will be 1, and then all other terms would be 0. What is this telling you? This is telling you that your system is in this particular state with 100% probability. Okay. So that's how a typical density matrix for a, pure state would look like. Okay. And the trace is 1. Yeah. Now consider this state. Okay. What this tells you, again, you have the basis vectors given as up and down vectors. But now you say that, you see, you have this combination and you have this combination, and you say that your rho, okay, is half of this plus half of this. What is this telling you? That means you are in the up state with some half probability, you are in the down state with some half probability, right? So now you are in a mixed kind of condition. So you can be in the up state, you can be in the down state with 50-50 probability. This becomes a mixed state. So from here, you can actually try to write it. So if you compare it with, what we had here, right, with this kind of form, whatever we had here. So if you compare it with this and try to write it in a matrix form, you would get something like this, right? Now here, if you do rho square, this is your rho. And if you do rho square, you would see that rho square is not equal to rho. So it's not a pure state. Okay. Again, if you want to find the trace, it's nothing but the summation of the vector diagonal elements. So half plus half will give you 1. Okay. So understand the difference. So here, when you're writing rho as, this outer product of these different terms in this basis, what you are saying is it's in down state with 50% probability, up state with 50% probability. So basically this coefficient, what you have here is associated with the probability. Okay. And this is a mixed state. But in the last case, what we had was different. Okay. This was just by looking at it and saying that, okay, half, half, half. So there are 4 states. So that's not correct. You are just writing the matrix elements based on whatever basis vectors you are choosing. Okay. But your system is in a single state defined by this description. So that's a pure state. Okay. Just be careful about this fact. Okay. Now, time evolution of density matrix. So if you remember, when we had initially, discussed about, like, in the classical description that when we had, we talked about Liouville's theorem. We said that in the phase space, if you have, certain number of microstates in the phase space, and then over time they are evolving with time, so you say that the density of the microstates would evolve in such a way that, you know the the volume remains conserved. And then from there we saw that if you consider the equilibrium state of a stationary condition where, things don't change over time, then the probability density should be a function of the Hamiltonian, right? And from there we could define all these different ensembles. So one was a microcanonical ensemble, which was for a constant, probability density. Then you had canonical ensemble, where the probability density was given as e to the power minus beta h, where h is your Hamiltonian. Then you had a grand canonical one, where it was given as e to the minus beta h minus mu n. So that means all these different descriptions of ensemble theory came up, but the underlying idea was that when you're talking about equilibrium condition or stationary condition where things are not changing over time, then rho, which is your probability density, should be a function of the Hamiltonian. Now, how does it come up in this context? Now, when we are talking about density matrix, how does it come up here? Okay, so here, if you consider a certain state psi, and you look at the Schrodinger picture where you allow your state to, evolve with time. So you're looking at the temporal change of your state psi. You can use the Schrodinger equation, which states that, if you are initially at state psi, so if you are in state psi at some point t, then del t of IH cut del t of psi is nothing but h psi, and this gives you the temporal evolution of your state vector. Okay, this comes from the Schrodinger picture of quantum mechanics itself, right? Now, you can also write a Hermitian conjugate of the same, okay? And now you consider the, stationary condition where you say that, the probabilities rho I do not change with time. So you say that ddt of rho I goes to 0, okay? Now, from here, okay, they merely determine how accurately we have fixed the state vector at the starting point t equal to 0. And afterwards, the system is actually evolving according to the Hamiltonian. So pi will stay constant as long as, there is some relation with the Hamiltonian, right? So you say that ddt of pi goes to 0. So if you now say that, there is no explicit time dependence, you try to write the fact that rho, which is your density matrix now, okay, this, you want to find the condition where this does not change with time. So IH cut ddt of rho vector, rho operator, will be given as what? IH cut ddt of this term here. You are just explicitly writing the density matrix. Okay. Now from here, you can actually use this Schrodinger equation. Okay, IH cut ddt of psi, you can write it as h psi. Okay. So what you get is this term here. So initially you had seen the Poisson bracket, right? Here what you are getting is a commutation happening. So it's a commutator, and it says that now rho and h commutes with each other. Okay. So IH cut ddt of rho is given as h rho minus rho h. Okay. So density matrix and Hamilton commutes with each other, which is telling you that, for this to, what do I say? It is just the analogous version of Liouville's theorem, which tells us that, so initially you had rho and the Poisson bracket of rho going to 0 kind of thing, right, in the classical description. So similarly here you have the, like, in terms of the matrix, this is how it looks like. Okay, from the measurement point of view, it tells us that if you operate the rho vector or the h vector, the order of operation does not make any difference, right? That's the commutation. That's what commutation means. Now, this happens when the density matrix is now a function of h. So again, you get back the same idea that initially in the classical description, you had the probability density becoming a function of the Hamiltonian. Here again, the density matrix is now a function of the Hamiltonian operator. Okay, like even in the matrix form, the basic idea remains still the same. Okay. Now, based on that same idea, now we can actually, extend what we have done for the different ensembles in the classical description to the matrix formulation now. Okay. So for a microcanonical ensemble, we did see that, all the, what do I say? The probability terms is given as 1 by omega. So where omega is your number of microstates, right? It's constant for all microstates. Okay. So that means if you define the density matrix, all the terms would be given as this. Right? It's a constant while you are in that energy range, otherwise it's free. Now for the canonical case, we remember that, this is how it looked like for the classical description, right? Where En were the different energy levels, and then this term here was nothing but Z, right? The canonical partition function. Now, how do you write it in the matrix form? So what is En? En are basically the eigenvalues, the energy eigenvalues, which are the eigenvalues of the Hamiltonian, right? So now in the matrix formulation, you can write it as rho vector, which is your density operator or the density matrix, is given as e to the power minus beta h vector, which is the Hamiltonian operator, divided by this summation. Now this summation in the matrix form is nothing but trace of e to the power minus beta h. So you have a h, which is a matrix. So if you want to write e to the power minus beta h, that will also have a matrix form. And then if you take the trace, that means the sum of all the diagonal terms, that will give you nothing but the partition function. So this is how you would write it in the matrix formulation. Okay. So explicitly, this is how you get it. So what you can say is trace is nothing but summation over n. You have chosen some basis vector phi n, set of basis vectors phi n. Okay. And then you are actually trying to find this inner product. Now what you can do is, h operating on phi n will e to the power minus beta h operating on phi n will give you e to the power minus beta en, because en is your energy eigenvalue, right? These are the eigenvalues of the Hamiltonian. So that means you can replace it like this. Okay. And because this is an orthogonal set of, complete, set of basis vectors, this would give you nothing but summation over n e to the power minus beta n, which is nothing but the canonical partition function. Similarly, if you want to find any expectation value of any quantity, that will be nothing but trace of rho vector into f vector. Okay, so this is how it would explicitly look like. It's just the mathematically, you're just representing the same thing in terms of matrices. The basic idea is the same, but this has huge applications in the sense that it makes calculations much simpler when you're talking about quantum mechanical systems, and that will be clearer when when we discuss further as the course proceeds. So if you want to define, suppose, the average energy, you define it as, expectation value of h, which is nothing but this term here. So again, you can write it as minus del beta of ln trace of e to the power minus beta h. Okay, remember that in the classical description, when we were talking about canonical ensemble, we had this equation, right? So it's same as this, but in the density formulation. Entropy can be written as minus k ln rho, which is nothing but minus k into trace of rho ln rho. Okay. Remember that when you do an expectation value, what do? You always multiply it with you used to multiply it with the probability density and then do an integration, right? So in the matrix formulation, this summation or integration is replaced by the trace of the matrix. And then you're actually again multiplying this rho with whatever quantity that you're trying to find the average of. Okay. Now for the grand canonical ensemble, again, it's the same as a canonical one, but you again have this extra minus mu n term, which is coming from the fact that in grand canonical ensemble, you can actually exchange number of particles. Okay, so this is similar to, so whatever, all the different questions that we typically solve for canonical ensemble or grand canonical ensemble, now if you want to do it in terms of the matrix formulations, this is how you can actually do it. Okay. So if you just look at some example, it says that find the canonical partition function and density matrix for a quantum harmonic oscillator. Now, what is this telling you? That So you know how the energy levels are for a quantum harmonic oscillator, like n plus half h cut omega. That's the different energy levels, right? So that means the matrix formulation. Now if you want to think about it, we know the energy eigenvalues is given as n plus half h cut omega. So that means you know the eigenvalues of the Hamiltonian, right? So that means you can actually try to find the canonical partition function for one particle. What will that be? It will be nothing but trace of e to the power minus beta h. Now, once when you are trying to find the trace, what will you do? You will do a summation over all the different, the diagonal terms, right? So that means now you are trying to, you would replace h. Basically, you would operate h on the different vectors, and that will give you the different eigenvalues itself. So basically, this is nothing but writing summation over n e to the power minus beta h cut omega n plus half. Okay, it's the same description that we have had previously. So now you can simplify it further to get an expression for the density matrix for the partition function, and this is same as what we had initially derived before. Okay, so now if you know the partition function for one particle, you can actually try to find for n particles. Okay, and if you want to find the density matrix, okay, so now you know z, you want to find the density matrix, right? So what will you do? Density matrix meaning finding the individual terms of the matrix, right? So you'd see that now you can actually write it as e to the power minus beta h cut omega n plus half by z. Okay, this is nothing but this term, right? You're actually operating this vector. When you are using e to the power minus beta h on some phi n vector, what will you get? You would actually get the eigenvalue into that vector back, right? So you can replace this by the corresponding energy eigenvalue. Okay, so rho n will be nothing but e to the power minus beta en, and then by z, right? Z. So I hope, I mean, what I'm meaning is when you use the rho operator, you have a h operator here. Okay, this term here is nothing but z. That is the already we discussed. Now you have e to the power minus beta h operator here. Now, what will the h operator give you when it operates on a basis vector? It would give you the energy eigenvalue, right? So that means rho n will be given as e to the power minus beta en by z. And that's what is being written here. E to the power minus beta into this term is nothing but en. The eigenvalue for one of the eigenvalues for the Hamiltonian. Okay. So that's how your different terms would look like. So I think this is all. If there are any doubts, you can, once you go through the video, if there are any doubts, you can, reach out, ask me. We'll try to discuss and solve questions. Basically, whatever we have been discussing for canonical and, or grand canonical, or all those in symbol problems that we had solved initially, you can actually try to see how you can represent it in the matrix formulation, and that will be a good practice to do. So they'll be very similar. The expressions will all be similar, but you can write it in the matrix form. Okay, and as we proceed in the course, you will see that this will be very useful when we talk about different quantum statistical systems. Okay, so yeah, I think that's it. So just try to practice that, if you have certain state, so just as you started with, writing the different, we did those questions of up, down, up, all those kind of things, right? So if you just do a practice of, if you are new with this pure state and mixed state concepts, then you can start with, trying to write, if you know your system is in up state, how will your density matrix look like? If it is in a combination of up and down, how will it look like? So all this kind of, practices, you can just try doing it. That will make things, much clearer. And if you already know about it, then it's fine. Just people who are doing it for the first time can actually, practice it a little bit. So I guess that's it. So thank you.